Continuing our discussion on solutions, we need to talk about some solute-solvent interactions. We know that oil and water don't mix, so how can we answer the question, will one substance dissolve another? To answer this question, we follow the little saying, like dissolves like. Polar will dissolve polar things. Nonpolar will dissolve nonpolar things. But what about ionic substances? What will they dissolve in? Well, ionic compounds are generally soluble in water because water is polar. What happens is we get these charged ends of the water molecules, and remember they have those partial positive and that partial negative. Well, they get attracted to the full charges, the positive and negative, of ionic compounds and kind of get in between them and keep those ions separated and into solution. Here are some pictures to help explain why water dissolves ionic compounds. First, we have our water molecule. And remember, oxygen's our electron hog, and so the electrons spend more time, so that oxygen develops that partial negative charge. And each hydrogen develops those partial positive charges. This next picture shows water's interaction with a salt like sodium chloride. So at first we have our water molecules, and they're that partial positive on that hydrogen is attracted to that negative of that chloride ion. And so what happens is it's going to be pulled away from those other charges in the crystal lattice. And then you have that chloride ion surrounded by those water molecules, each of the hydrogens pointing in toward it. If we look at the other side, oxygen has that partial negative charge, and so it gets attracted to the positive of the sodium ions and kind of pulls it away from the crystal lattice. And then you have that sodium ion surrounded by the water molecules. Notice that the oxygens are all pointing in toward it because that's where those partial negatives attracted to that full positive. Now, since those ions are surrounded by water molecules, they're not attracted to each other and will stay in solution.
Nonpolar solvents generally do not dissolve ionic compounds because they have no charges. They're sharing their electrons equally, so there is nothing to attract the ions away from what they're already attracted to. Liquid solutes and solvents. So if we have two liquids, we would describe them as either miscible or immiscible. Immiscible means they are incapable of mixing. This would be like oil and water. One would sit on top of the other one and there would be no mixing. That would be non-polar oil and polar water. Nothing to attract one another. Miscible means that they're capable of mixing. Now, carbon tetrachloride is a very, very popular non-polar solvent. So if benzene is miscible in carbon tetrachloride, then benzene is also non-polar. Effects of pressure on solubility. Increasing pressure increases gas solubility. This is what they have to do in order to make your soda. Remember, they're sold under pressure. You can't squeeze an unopened 2-liter. That's because they have increased the pressure to get the gas, the carbon dioxide, to stay in solution. Pressure has little effect on the solubility of liquids and solids. Henry's law applies to gas-liquid solutions at constant temperature. Carbonated beverages contain dissolved carbon dioxide. The carbon dioxide is forced into solution by increased pressure. If you open an unopened soda, you'll hear that psh sound from the release of the pressure, and then you'll notice within the liquid, the gas starts to come out. You see all the bubbles. So that's called effervescence, the rapid release of a gas from a gas-liquid solution due to an increase in pressure. And that's a little bit summing up Henry's law. Now, increasing temperature generally increases the solubility of solids and liquids. Not always, but generally does. For most things, it does. Sodium chloride stays pretty constant no matter what the temperature is of the water. Its solubility doesn't really increase, but for most things, it does. Now, for gases, increasing temperature decreases gas solubility. So the higher the temperature, the more motion, the more kinetic energy those gas particles have, and the less likely they are to stay into solution. They're going to have energy enough to break those attractive forces. When a solution is formed, an energy change occurs. Heat is either absorbed or released. When making a solution, solvent and solute particles experience a change in attractive forces. And that is the reason why heat is either absorbed or released. So, for some things, it is an endothermic process. That means as you mix it with water, it's going to end up being colder. With these, increasing the temperature would definitely increase the solubility. Negative heats of solution, heat is released. These are exothermic. Sodium hydroxide is very exothermic when it comes to its heat of solution. So it produces quite a lot of heat as it experiences that the change of attractive forces. And the Na stops being attracted to the hydroxide and is now attracted, each of them are attracted to water. These are exothermic. These don't require the solvent to be heated in order to increase that heat of solution or increase that solubility. Now we have molarity. This one we talked about before, and you should be pretty familiar with molarity. Moles solute over liters of solution. I have a couple of problems in here. I'm not going to work through these. Again, you should know how to work with molarity. We do it all the time, and solving for different things within molarity. These are easy types of problems that will and can appear on that AP exam. So make sure you don't miss an easy problem by neglecting a molarity calculation. This one has to deal with dilutions, M1V1, M2V2. I like to say MCVC equals MDVD. The C means concentrated and the D means dilute. So this one, how many milliliters of 5 molar potassium chloride solution would you need to dilute to make 100 milliliters of 1 molar KCl? This is my concentrated because its molarity is higher than this one. So this is my dilute. So I want to know how many milliliters of my concentrated. So I'm going to be looking for VC. And this is often how these problems are done. This is what you have to do in order to make a dilution in the lab. So we'll do this calculation first. It's going to be the molarity I want the dilute solution to be times the volume, which is going to be 100 milliliters, and divided by the molarity of my concentrated, so 5. Molarity cancels out. My answer is going to be in milliliters. So I need to add 20 milliliters of my concentrated solution to a 100 volumetric flask, and then I need to add fill it up with water to the 100 milliliter line mark. Again, these types of problems will be found on the AP exam. You will have to do them as you go into chemistry labs and making those dilutions.